After having studied Newton's three laws of motion, we will now look at law of conservation of linear momentum. The law states that if no external forces act on a system of two colliding objects, the total linear momentum of the system remains constant. So this is what the law states, and we will go into the depth of this law and try to understand it, starting from the fundamental concepts about linear momentum. We know that linear momentum, denoted by P, is equal to mass of the body into its velocity. And according to Newton's second law of motion, force is given by the rate of change of momentum dP by dt. So here we are talking of a system of two colliding objects. So let us say we have two objects. Let's say this is object 1 and let's say this is object 2. Let me take a bigger object. This is too big. Object 2, and they are on the verge of collision. So I'll say this is object 1, this is object 2. Mass is say 1 kilogram and this mass is, let us say, 4 kilogram, and object 1 is moving in this direction with say velocity of 2 meters per second, and object 2 is moving in this direction with a velocity of 3 meters per second. So this is the situation at a given instant of time. So let us say this is the situation at a given instant, say 5 hour 10 minute 21 second and 0.1. So this is the situation at this particular time when they are just on the verge of colliding, when they collide. And what I can do is I can have what happens to this entire system in the next second. So let's say I take both these objects again. So this is, I'm showing the first object again, and this is the bigger object, 4 kilo object, and let's say they collide and then they start moving in the opposite direction. So now let us say this object is moving in this direction with a velocity of 6 meters per second, and in this with a velocity of 2 meters per second. 2 meters per second. The masses of course remain same, 1 kilogram and 4 kilogram. This is object 1 and this is 2, and this is the situation at say 0, 5, 10, 21, 0, 2 hours. So there's a very small gap. Time is very, very small between these two incidents, and here both of them collide and here they are going away from each other. Now, the total momentum of this system initially is mass into velocity of both the objects. If you take, so the first object is of mass 1 and its velocity is 2, plus here it is mass is 4 and velocity is 3. So this will be 2 plus 12, that will give me 14. And right now I'm not worried about it, so I'm simply taking the sum of the total momentum of the system over here as 14 units. And after the collision occurs, the sum of the momentum will be, in this case its mass is 1 and velocity 6, plus here 4 into 2, 8. So this will give me a value of 6 plus 8, 14. So 14 units. So this is what happens based on the law of conservation of momentum. That the total momentum of the system, this is the total momentum of the system, 14, remains constant, remains same when no external force acts on it. So this is the most important part of the law. When no external force acts on a system of two colliding objects, the total linear momentum of the system remains constant. Now you must be wondering that these two objects collided, so how can we say that there is no external force? The stress is on the word external. This force which came into being when these two collided was the internal force between these two objects. There was no external force. To explain further, when they collided, supposing there was another external force which acts onto this object in this direction, that would be an external force, and that would change the velocity of this object too, because it would push this object in this direction. Similarly, if there would be another force acting on this, external onto this, like this, it would change the velocity which we obtained over here as 6 meter seconds per second. It would not be 6 meters per second. It would change because of this force. So that is what we mean by an external force. So when two objects collide with each other, there is no external force acting on them. And in that situation, the total momentum remains constant or same. So this is how we can explain or understand the law of conservation of linear momentum. And I also want to go back over here and talk about that we're talking about law of conservation of linear momentum. So here we're talking of objects moving in a plane. We're not talking of objects which are moving in 3 dimensions. Later on, when we study rotational motion of body, we will also look at law of conservation of rotational momentum. There we will look at objects which are moving in a circular path, and they're moving in 3 dimensions. So this is with regard to linear momentum. Right. So I've taken an example, and of course you would have guessed that I manipulated these values so that the total sum comes out to be 14. So it is not that I took up random values and it came out to be 14. So, that is something which we need to keep in mind. But this is what would happen if we had this situation. If we look at this law in general terms, then this is what I would say. This 1 into 2, I can call it as P1I. That is the initial momentum of the first body. And this would be P2I, the initial moment of the second body. Similarly, over here, 1 into 6 would be P1F, and 4 into 2 would be P2F. And if I find out P1F minus P1I, I can call it as dP1, the change in momentum of the first body. Similarly, if I find out P2F minus P2I, that would be dP2, the change in momentum of the second body. And if I divide this by time dt, the very small time during which the collision happens, dt, let's say I divide this by dt, then this would be the force acting on the first object, because as we discussed, force is rate of change of momentum. So this is the rate of change of momentum of the first object. So this will be force F1, the internal force which is acting between the two objects, and dP2 by dt will be F2, the internal force acting between these two objects. And please note that these forces that we are talking about are the internal forces. When the two objects collided, by Newton's third law of motion, they applied equal and opposite force onto each other. And these two forces were F1 and F2. So F1 force acted on body 1, F2 acted on body 2. Now, according to Newton's third law of motion, these two forces, the internal forces, can be written as F1 plus F2 equal to 0, because they are equal and opposite, F1 and F2. Therefore, I can write down dP1 plus dP by dPt. Of course, I should have put the vector sign over here because dealing with vectors, plus dP2 dt is equal to 0. So I get this equation, the total sum of dP1 and dP2 is equal to 0, and if I write this in general terms, I can write dP by dt equal to 0. That is, there is no change in momentum. dP represents change in momentum. The change in momentum is 0. And that happens when there is no external force acting on the system. As we saw, F1 and F2 were the internal forces which came into play. And when we have that situation, when F external is equal to 0, we can say dP by dt equal to 0. That means the total momentum of the system remains constant as dP is equal to 0. So this is the mathematical expression for the law of conservation of linear momentum. Thank you.